In this presentation we'll look at one of the most important areas of switching, and that is the usage of the spanning tree protocol, or STP. Basically, the main concept that we have with the spanning tree protocol is the concept of a bridge. And the main objective of a bridge is to learn the MAC addresses on either side of the bridge, so that when a source machine sends to a destination which is on another port of the bridge, it will automatically forward it through. As far as the machines know, the bridge is transparent in that the machines on either side of the bridge appear to be on the same local network. So that means that an ARP packet sent by one machine will be sent to others on the other side of the bridge. And there is now a standard called the 802.1d. And the advantage of a bridge is that it avoids loops, and that bridges intercommunicate and find the best route to a destination. It also learns the stations on either side of bridges and is able to filter based purely on layer 2 MAC addresses. So in this case we have a bridging table. The bridging table has added that on port 1 there are two machines, MAC 1 and MAC address 2, and on the other side on port 2 there is MAC 3 and MAC 4. When this machine wants to send a data frame to this machine, it sends its destination MAC address, which it should have already discovered through an ARP request. So the data frame is sent, and the bridge picks up the data frame and forwards it to the next port, doesn't change any of the details of the data frame, and then forwards that directly. No other machine apart from the two which are involved in the communications should be able to see the communications. As it is a switch network, we can have multiple communications at any given time, but the bridge itself will only allow one communication at a time, of course. So on a switch adopts this idea and has what's called CEM, or Content Addressable Memory. We hardly ever see bridges as part of networks now, and normally what we use is a switch. In this case, we have a switch which connects the two machines on either side, and then we have an interconnected switch which is connected through two ports. It is now up to the switch to identify the nodes on either side and learn their addresses. So in this case, its CEM table has MAC 1 and MAC 2 from port 1 and MAC 3 and MAC 4 on the other port. The switch will then forward the data frames across between ports. At any point we can look at the CEM table with the show MAC address table dynamic, and dynamic means the ports, the MAC addresses of the nodes that it's actually learnt. So in this case it can assign them to VLANs. So we can see here that on the ports we have 3 addresses learnt on the gigabit 02 interface, and these have been learnt dynamically. These identify the MAC addresses and these identify the VLANs. It is important that a switch does not forward a data frame from another VLAN for security reasons. Thus it will only forward based on the VLAN which it is in and the destination MAC address. If it cannot match these two, then it will not forward the data frame. A key concept is that machines obviously are connected and disconnected onto a network at a regular basis. So it is important that addresses are aged out, and we typically have an aging process where all the MAC addresses have to be relearned after a certain amount of time. So we can see in this case, once MAC 2 has been aged out because the node isn't connected anymore, it will eventually be deleted from the CEM or aged out. An extremely important part of the spanning tree protocol is to make sure that we do not have multiple routes between a source and a destination. In this case, we've created a backup route between each switch, just in case one of the switches becomes inoperable. So you can see here that we could go from MAC 3 to the other MAC 3 on the other side via this route, or we could go via this route here. So there are now multiple routes. So it is up to the spanning tree protocol to decide which route is the most efficient based on certain parameters. In this way, we can set the complete picture for the whole network up so that there is only one route to a destination. As we'll see, at this layer here, we typically have redundancy built into it. The access layer is less important, but at the distribution layer, we typically have redundancy, so the spanning tree protocol must analyze the routes and decide the best one. Then all the switches are kept up to date on the optimal routes. The way that the spanning tree protocol works to be able to get this coherent picture of the network is to send what are called BPDUs, or Bridge Protocol Data Units, and these are typically seen as broadcasts into the network and advertise when there is a change in the topology, such as a new connection or a connection being deleted. The main objective is obviously to detect and eliminate loops, to hopefully detect where there are faults and to find alternative routes, and to fine-tune the network performance and finding optimal routes. So when a new route a new machine is added, or a new switch is added to it, or where we have different switch cost ports, a BPDU is sent. When this happens, when an update is sent, certain ports can be set into either blocking phase or a forwarding phase, and that can stop data from being transmitted into the network. Some of the key terms that we have is that we have a concept of a bridge identifier, and that allows us to create a unique bridge ID. Typically it's the bridge ID priority and also one of its MAC addresses. It then uses this in an election process to find the switch which is seen to be the root of the network. Each port themselves has a port priority, and if there are multiple ports on the switch, then a port can be allocated as having a higher priority than another one. There is also a port cost, and a port cost will help to calculate the optimal route, and in that the higher the bandwidth possibility for the port, the lower the port cost. So when routes are calculated, then the port cost can be taken into account. So when we select the port that will be used for forwarding, basically it's the lowest accumulated port cost for the whole of the route. So in this case we might have a port cost of 2 here, 2 here, possibly a 4 here, say a 19 here, a 100 here, and so on. So to calculate the routes we basically add them up. We have 19 plus 2 gives us 21. In this case we might have 4 and 2 and 100, so the first route would win. With inside the bridge protocol data unit as defined in 1D, we have this bridge protocol ID, that's the bridge ID, version number, some flags, the route identifier, which we'll see is important, the bridge ID, port ID, and so on. Basically what we have is that we define for spanning tree an election process, and it's up to the election process to define the route switch, and there's this route switch in which the calculation is made on the optimal route. And basically it is the one, it will be the switch which has the lowest identifier, the lowest bridge identifier, and if all the bridges have the same priority, the same bridge ID, then it is the port which has the lowest MAC address. So we can see here that the switch ID is defined by its priority, which makes up 2 bytes. We can thus have up to 16,000 addresses, and then we have 16 bytes for the MAC address. Once the route switch is elected, then routes are calculated based on the route switch. So we can see here this allows us to define our spanning tree. So in this case, on this switch we have a VLAN 1, and it has a priority number of 10. And then we can actually define the port costs on each of our ports. So in this case we go into the first interface and we define a port cost of 32, and for the second Ethernet port it has a lower port cost of 31. Now that we've determined the route switch, each switch must determine their route port. For this, they calculate the total accumulated cost for them to get to the route switch. If there's a tie on this, then they will use the lowest ID, bridge ID, for a neighbouring switch, and use that as the route port. If there's a tie on the IDs, it will then use the port with the lowest priority. Again, if there's a tie on this, it will basically just use the lowest port number on the switch. A key factor in spanning tree is the amount of time it takes for it to settle down and to have some form of convergence where all the switches actually have a coherent picture of the whole network. This can take 30 to 50 seconds and happens after the route switch has been selected and also the route ports. The first phase that happens is basically a lockdown for the network, where all the ports go into a blocking phase and they do not listen to any data frames. So no traffic can flow in the network while this happens. and the ports only listen to the BPDUs. It typically takes about 20 seconds. After this, the ports go into a listening phase, but they only listen for paths that go to the root and do not forward any data frames. After this, the ports will go into a learning phase where they learn the MAC addresses of the nodes which are connected to themselves, but again they do not forward any data frames. After this, they will go into a forwarding phase, which is the normal phase where they learn and forward data frames. The ports can also go into a disable phase, typically where there's a broken connection or when an administrator has disabled a port. An enhancement to STP is called port fast, and the configuration of port fast is seen here. We enable it on an interface with spanning tree port fast, and then in our running configuration we should be able to pick it off. With port fast, we exclude ports from the main setup for the STP convergence. Thus, these ports do not go through any blocking, listening or learning and forwarding phases, but go straight into a forwarding phase. So this shows an example of our spanning tree configuration. We can see here a summary for it, and we can see here that port fast has been disabled, and the basic activity for our basic phases, we can see here blocking, listening, learning and forwarding. We can also look at it for individual interfaces with show spanning interface, and in this case FA02. There are various enhancements to the STP protocol. One of them is BPDU guard, and that is to stop an intruder from injecting BPDU packets into the network and to obviously cause disruption. So in this case we can set up on certain interfaces whether we have a guard on this and can actually disable the port. We can also have a basic filter. In this case it might be that if it receives more than 10 of these packets, it will disable port fast and return to normal operation. Another enhancement to this is called an uplink, where a redundant link is used to reduce the convergence time. Typically this can be less than 4 seconds. So we have, with this, we require the uplink is enabled on the switch, and we can see here this is our uplink setting for spanning tree. One of the ports should be blocked. As we've seen, the basic protocol for STP can take between 30 to 50 seconds to converge. An improvement to this is rapid STP, and that's defined in the 8021W standard. And with this we can get much faster convergence, typically in less than a second, as opposed to the 50 seconds which we get with 8021D. This type of setup is obviously important for real-time applications which cannot stand these long convergence times when there's a disruption on the network. Another enhancement is multiple spanning tree, and again this is used to provide rapid convergence. It's typically used with multiple VLANs to be able to create a single spanning tree instance for the whole network. So we can see here the configuration of MST, and for this we define an instance number and the VLAN, and then we apply it on to the whole of the switch with the spanning tree mode MST. Another enhancement is with Etherchannels, and with this we can actually group multiple streams into a single Ether channel.